Hello, PreCalc kids. Today we're looking at a review of graphing rational functions. We looked at this in college algebra. So we're going to look at a quick review in this lesson of graphing rational functions. Notes out, and here we go. Graphing rational functions. Now remember one thing, you can always check these on your calculator, but we're looking at how do we graph these without using your calculator. And we need to define what is a rational function. A rational function is a function that is a quotient of two polynomial functions. Easiest one we can look at is y equals 1 over x. In our graph of y equals 1 over x, right, easy point to look at is 1, 1. If we look at 1, we get 1. If we get 2, we get 1/2, 1/3, 1/4, 1/5 as we go out. But as we get closer to the y-axis, what happens? If we look at 1/2, we multiply by the reciprocal and we get 2. 3 goes up, and so this graph goes up, never reaching the axis. The same thing happens on the negative side, going that direction. And this graph gives us our example. We get two asymptotes. Here the asymptotes are just the axes themselves, the x-axis and the y-axis. An asymptote is a line to which a part of the function approaches. A vertical asymptote is a vertical line. The horizontal asymptote is the horizontal line. A graph could have no asymptotes, could have just a vertical asymptote, could have just a horizontal asymptote, could have both. So there's different things that could happen. Could also have a slant asymptote. We talked about that in college algebra as well. Here's how we're going to define these mathematically. The vertical asymptote is the line x equals a, is the vertical asymptote for the function as f of x goes to infinity or f of x goes to negative infinity as x goes to a from either the right or the left. So again, the closer we got to 0, this graph is going down to negative infinity from the left. As we get closer to 0 on the x-axis, going from the right, this graph takes off to vertical infinity. And so that value a here was 0. For the horizontal asymptote, we're looking at as x goes to infinity, what happens to, and it goes to a value b, which gives us a horizontal asymptote. Let's look at some examples. Determine the asymptote for the graph for the function f of x for 3x minus 1 over x minus 2. First thing we want to find are the vertical asymptotes. We find the vertical asymptotes using this rule. It's where the denominator equals 0. So the vertical asymptote is where the denominator, x minus 2 equals 0. So our vertical asymptote has to be at 2. So there's our x equals 2 vertical asymptote. That was the first thing we did in college algebra when we were graphing rational functions. The second thing is the horizontal asymptote. We actually had 3 cases, but for this, we're just going to kind of do the shortcut. And that shortcut is we're going to divide each term by the highest power of x and let x go to infinity. So what does that mean? So we're going to take the function f of x, and we're going to divide each term by the highest power. Well, that highest power is just an x, not the coefficient, just the powered variable. And so we're going to divide each term by x. So 3x divided by x minus 1 over x, all divided by x over x minus 2 over x. And we're going to see what happens. We want to set x goes to infinity. So as x goes to infinity, what happens? Well, in this case, it doesn't matter what x is, x and x will cancel. That divides out. So that leaves us with 3 minus. What happens here is x goes to infinity. This term, 1 over x, does what? Well, think about getting really big. 1,000, a million, 1 over 1,000, 1 over a million, 1 over a billion. This term goes to 0. X over x goes to 1. Again, this term, as this number gets really, really big, as x goes to infinity, this one also goes to 0. And what's left? Well, we get 3. Therefore, our horizontal asymptote is at y equals 3. Now, how can we use that to graph our equation? So we know we have a vertical asymptote at x equals 2. So we're going to go to 2, and we're going to put a dashed line for our vertical asymptote. And we know at 3, we have a horizontal asymptote. Now remember, a graph can't cross a vertical asymptote. It can possibly cross the horizontal, but that's only in some rare situations. So keep that in mind. From there, how do we know where the graph lies? Well, from there, we want to use some test points. So for test points, for example, here's 2. So let's look at 3. Really, we just want to know is the graph above or below this horizontal asymptote. So if we look at 3 and we plug 3 into the function for x equals 3, we would get 3 times 3 is 9. 9 minus 1 is 8. 3 minus 2 is 1. So we get a value of 8. That's obviously going to be above. So the graph has to look like this. And then for the other side, the question is the graph again above or below this horizontal asymptote? Easy test point is 0. If we plug in 0 and 0, we get negative a half. We get positive a half. And so this graph has to be below the asymptote. So it's going to look something like that. Again, we're not trying to be exact with our graph. We're just trying to get close. So there's our main 2 rules. To find the vertical asymptote, we're setting the denominator equals 0. For the horizontal asymptote, we're going to use our trick to divide every term by the highest powered variable, and then let that run out to infinity. In college algebra, this was actually case 2, I think, where if the degree is the same, the horizontal asymptote is going to be the coefficients, if you remember back that far. Checkpoint 2, use the parent graph f of x equals 1 over x to graph each function. Describe the transformations that take place. Identify the new location of each asymptote. Letter A is g of x is equal to 1 over x plus 5. So here what happens? Well, our vertical asymptote, again, is the denominator set equal to 0. That's x plus 5 equal to 0. Therefore, our vertical asymptote is at x equals negative 5. Also recall our original graph, f of x is 1 over x. That's the graph that uses the axes as the asymptotes, and I just realized that's covered by my photo. So that's our parent function. So what happened here with our graph? We also want the horizontal asymptote as well. To get that, we're going to divide each term by the largest variable term. That's 1 over x divided by x over x plus 5 over x. And what happens? As we set x go to infinity, well, 1 over infinity, that goes to 0. X over x is 1. 5 over infinity, that goes to 0. 0 over 1 is 0. So our horizontal asymptote is still at y equals 0. So here's our graph. Now our vertical asymptote, what did it do? It shifted left 5. Our horizontal asymptote is still the y-axis. And here's our graph. Sign didn't change, so there's still our graph. So what happened? Again, this is going to be kind of the inside the number h, and so it's opposite. So we shifted left by 5. It's an opposite of what's in that denominator. Why is it opposite? Because we have to solve for x. And how do we solve for x? Well, we take the opposite of the number. That's why our shift is going to be the opposite. Letter B, what happens if we take a negative 1/2 x? Or basically, what does the negative do? So let's again look at our asymptotes. Our vertical asymptote is setting the denominator equal to 0. That is 2x equal to 0. So that's x equals 0. That didn't change. So our vertical asymptote is still the y-axis. For our horizontal asymptote, we're going to divide each term by x. Again, not the coefficient, just the powered variable. So that's negative 1 over x divided by 2x over x. And as we set x go to infinity, what's negative 1 over infinity? Well, that goes to 0. X over x is 2. 0 over 2 is 0. So our horizontal axis is still the x-axis. However, what did change? One thing is the 2, so the steepness at which the graph grows is going to change. Also, because we have a negative, what's going to happen? We saw this earlier in the chapter. If we multiply a negative by the whole function, it's going to flip it how? It's going to flip to the left and right. It's a reflection over the y-axis. Think about it. If we plug in a 1, no longer now are we above, we're actually down below the axis. And no longer is this one down here, this one's up here. And that's generally going to be what happens when we multiply the negative. Again, it's a flip, like look at our original. Here's our original, y equals 1 over x. There's the flip over the y-axis. Let's see here if we can predict how our graph is going to change. Now, obviously, we have a number up here. We'll see if that does anything. Here, what's the horizontal shift going to do? Well, we're going to shift, h has to be 3. So we're going to shift our vertical axis right 3. We know that because our vertical asymptote is the denominator equal to 0. And that's x equals 3. So 1, 2, 3, there's our vertical asymptote. Our horizontal asymptote, again, we're going to find by using our trick. The biggest degree variable is x. So we're going to take each term divided by x, and we're going to set x goes to infinity, see what happens. Well, what happens to 4 over infinity? That gets really small, so that goes to 0. X over x is 1. 3 over x, and that goes to 0. 1 over 0 is 0. So again, our horizontal asymptote is y equals 0. And then what happens with the 4? Well, this is going to be a stretch. So remember, if a is greater than 0, or a is greater than 1, it's a stretch. If a is greater than 0, less than 1, then it's a shrink. So this is going to be kind of a bigger graph, more further away. So what transformation do we have? We had a shift right of 3, and we had a stretch of 4. And letter D. Now let's see what's going to happen. Right, just using the rules we talked about before, we have a negative. What's the negative going to do? Well, that should result in a flip about the vertical axis. We have a 6. That's going to be a stretch. We have a plus 2. What's that going to do? That's going to shift our vertical axis left 2. It's the opposite. And we have a minus 4. That's our k. And that should drop the horizontal axis by 4. Let's see if all of that stuff happens. Our vertical asymptote is set the denominator equal to 0. That's x plus 2 equals 0. So x is negative 2. So in our graph, there is our horizontal shift, left 2. Next is our horizontal asymptote. That's our trick of dividing each term by the denominator. And so that's going to be negative 6 over x all over x plus 2 over x minus 4. We're going to set x go to infinity. What happens? Negative 6 over x goes to 0. X over x goes to 1. 2 over x goes to 0. And we still have the minus 4 out here. So all of that's gone, and we're left with y equals negative 4. There's our horizontal shift downward of 4. So we are down 4. We also have a stretch of 6 because of the 6. And we also have a reflection because of the negative. So where does that put us? Well, that puts us over here because we're flipped, and down here. Again, you can always check that by graphing it on your calculator. So there's practice of finding the asymptotes using the transformations to graph rational functions. How can we use these in practical applications? Let's look at this chemistry problem. Write the function as a transformation of the parent function, f of x equals 1 over x. Graph the function and identify the asymptotes, interpret their meaning in terms of the problem. All right, so the first thing we want to do is find our vertical asymptotes. That's going to be where the denominator is equal to 0. So 50 plus x equals 0. Therefore, x is negative 50. So in our graph, somewhere we're over here left, negative 50. There's our vertical asymptote. To find our horizontal asymptote, again, we're going to use our trick. The largest variable term is x. So we're going to have 500 over x plus 4x over x all over 50 over x plus x over x. Again, we want to set x go to infinity and see what happens. So 500 over infinity, the bigger and bigger that number gets, this goes to 0. 4 over x leaves us with 4. 50 over x goes to 0. X over x goes to 1. So we have a horizontal asymptote at 4. Then we can graph our function. This is a positive rational function. So this graph will be up here, and this graph is down here. So interpret the meaning in terms of the function. So this was a problem about molarity. If you actually went back and read the problem, the more we add, or whatever we're adding, the more we add, the closer what happens, the closer the solution gets to a molarity of 4. And really what can happen, it can never really be negative. So really we're just looking at this part of the graph in a practical sense. Recall we also in college algebra talked about slant asymptotes. The slant asymptotes occur when the degree of the numerator of a rational function is exactly 1 greater than that of the denominator. We can define that mathematically as an oblique line. That's just a slanted line. Is the slant asymptote for the function f of x of the graph of f of x approaches L as x goes to infinity or as x goes to negative infinity. What do we do here? Well, here we're going to use division. You can either use synthetic division or you can just use regular division, whichever one you want to do. We'll review both. But we want to divide this. We know this is the case. This was our third case in college algebra. The degree of the numerator is squared. The degree of the denominator is 1. Now, you could actually also use our rule of dividing by x as well. And I'll try to sneak all of that on here to show you how all of that works. Let's use good old division. 2x squared minus 3x plus 1. What number do we need to multiply by to get 2x squared? Well, that's 2x. So it goes in the same linear column. We multiply back. 2x times x is 2x squared minus 4x. Then we need to change signs to subtract, and that gives us 4x minus 3x is x. Now we drop down to 1. What do we multiply x by to get x? Well, that's 1. And then we're going to multiply back. That's x minus 2. We're going to change signs. That gives us 3. So that gives us our remainder, 3 over x minus 2. And so what happens was x gets bigger and bigger and bigger, right? As x goes to infinity, this thing goes to 0. So what's our slant asymptote? It's y equals 2x plus 1 is our slant asymptote. Let's see if we can get that using synthetic division. For synthetic, we're going to opposite this number, so 2. Then we're going to write the coefficients, 2, -3, 1. We're always going to drop the first number. That's 2. 2 times 2 is 4. Then we just add. We don't have to do subtract because that's why we changed the number. Sign's going to be the same. There's 1. 1 times 2 is 2. 2 plus 1 is 3. And there's our y equals 2x plus 1 plus our remainder of 3 over x minus 2. Again, as x gets really big, this thing goes to 0. So again, here's our slant asymptote. There's the second way to do that. The third way is to divide each term by the biggest variable term. Is that right? No, because that would make it not right. So we're going to stick with those two methods. All right, here's our graph. Notice we still have a vertical asymptote. The vertical asymptote is at x minus 2 equals 0, which is x equals 2. So we do still have a vertical asymptote. But now we have a slant asymptote, and that's at y equals 2x plus 1. So there's 1 for my intercept, the slope of 2. Takes me there and there. So there's our slant asymptote. And it's positive, so we're still going to be up in this quadrant, but this is going to approach the slant, and then this one's going to come up and then drop back down. And again, you can always check that on your calculator. There's using a slant asymptote. Let's look at another example. X plus 2 times x minus 3. Notice what happens here. Well, here in the function, there's 2 x minus 3's. They cancel, right? Because x minus 3 over x minus 3 divides to be 1. So we really get x equals x plus 2. Well, that's our slant asymptote. But this is still the original function, right? When we plug numbers in, that's still our original function. So we have the equation, x plus 2, 1. But something special happens at the vertical asymptote. This is actually not a vertical asymptote, but something special occurs at x equals 3. Because these two things canceled, the x minus 3's, we get a slant asymptote, but at x equals 3, this is when we get a point discontinuity. So whenever we have linear terms that cancel, we end up with a point discontinuity. So this function is continuous everywhere except at x equals 3. There's just a gap in the line, just a hole, because that canceled. And so anytime we plug in a 3 minus 3 is 0, you can't divide by 0, resulting in just a tiny gap in the line. And that's our point discontinuity. It occurs where common factors divide out. Let's look at example 5. Well, we just talked about point discontinuity. So what do we notice? Well, we have the same term, x plus 3 over x plus 3. So it has to be a point discontinuity at, when we need to solve for it, x equals -3. And then we're just following the same rules. Our vertical asymptote is where the denominator is equal to 0, and that's just using the 0 product rule. So we're going to set all of these equal to 0, x times x plus 3 times x minus 2 equals 0. So that's x equals 0, x equals -3. We actually just define that as our point discontinuity, though, and x equals 2. So if we look at our graph, we know at 0, there's a vertical asymptote. We know at 2, there's a vertical asymptote. And then because x equals -3 was the division of the same linear terms, then that's not a vertical asymptote, that's already our point discontinuity. But it does occur at -3. So something happens there. Wherever that graph appears is our point discontinuity. Then we want to look at our horizontal asymptote. Because the degree of the denominator is greater than the degree of the numerator, that's going to be at y equals 0. That was our first case. Right, everything's going to cancel. And so y equals 0. Well, just to show you, this would cancel. So we're left with x plus 1 over, multiply this would be x squared minus 2x. So I just multiplied that out. And then that's going to be x over x squared plus 1 over x squared all over x squared plus, minus 2x over x squared. 2x, sorry, just x squared. That goes to 0, that goes to 0. So we have 0 over 1 minus 0, which is 0. So there's our y equals 0. If you didn't believe me. And so what happens, so there's our slant asymptote. And so what happens here, again, you can use test points. So we can look at 3. If we plug in 3 into this, we're going to get a value that's positive. So we have to be above the axis. Has to look like that. If we plug in 1, we're going to get a value that's below. So this has to be something like this. And then for the point discontinuity, this is actually going to cross the axis and then come back, which is kind of weird. But remember, a graph can cross a horizontal asymptote and then come back, which is what happens there. All right, let's look at the graph. 2 more to go. So what do we need to do in this case? Well, we want to factor this first. So if we factor this, signs are same, both minus. It's got to be x minus 3 times x minus 3. Factor this, signs are different. It's got to be x plus x minus. Multiplies give 6, subtracts to give -3 is minus 3 plus 2. So there's a point discontinuity at x equals 3. Our vertical asymptote is where x equals -2. We already had 3, but that's our point discontinuity. So -2, there's our vertical asymptote. The horizontal asymptote, that's going to be everything divided by x squared now. And we want x to go to infinity. Squared over squared is 1, 0, 0. This is 1 and 0 and 0. So our horizontal asymptote has to be at y equals 1. We can look for zeros. Zeros are where the numerator equals 0. So there has to be a 0 at x equals 3. That's where it crosses the x-axis. We could have done that in previous questions as well. But what do we know about x equals 3? Well, it is a point discontinuity. So actually, this is an open circle at 3. And so that gives us an idea of where our graph lives. It actually lives down here and up. Again, we can use test points to see if we're above or below that horizontal asymptote. And this one's above. Or you can graph it on your calculator. Last one, the big one. Y equals this thing. First, what do we notice? We have the same linear term, so there's a point discontinuity at x equals -2. The vertical asymptote is where the denominator equals 0. So for x, we have a 0. For this, we need to solve. And so we'd have x minus 4 quantity squared equals 0. That's x minus 4 equals 0, so x equals 4. and x equals -2, but that's already our point discontinuity, so that doesn't really count. Our horizontal asymptote, again, the degree of the denominator is going to be greater than the degree of the numerator, so that's going to be y equals 0. We can check for any x-intercepts or any zeros by setting the numerator equal to 0. That's -2 and 3. So we're going to use all of that information to graph. We have a vertical asymptote at x equals 0 and 4. Our horizontal asymptote is at y equals 0. And we know we have zeros at -2 and 3. Again, we can use test points. If we look at like 5, it's going to be above 0, so the graph has to be up here. For here, then the question is, how does the graph work? Does it go positive down to negative, or does it go up here down to negative? Again, we use a test point like 1, and 1 we get a negative, so the graph has to come back up this way. And then again, we can use a test point of -1. We'll see the graph is above. So it comes through. This is a 0, so it has to cross, and it comes back to the axis. So there's a review of graphing rational functions. Here's your homework, page 186, 14 through 40, and 43. Have a good day, Maroons. See you in class.